So what if I told you that a gentle breeze, something you barely even notice, could literally tear a massive steel bridge to pieces? I know, it sounds completely impossible, right? But it's a perfect example of the invisible yet incredibly powerful world of waves. I mean, they're the reason you can hear my voice right now, the reason you can even see this screen. And, as we're about to find out, they are the key to some of the most amazing achievements in modern science. Here's the game plan for how we're going to connect all these dots. We're going to start with that dancing bridge, believe it or not. Then we'll break down the fundamental physics. What is a wave, really? From there, we'll pop into the lab to see how scientists actually measure these things. And finally, we'll see how all that knowledge lets us do everything from navigating the deep sea to looking inside the human body. It's going to be quite a ride. All right, first up, let's travel back to the year 1940. We're about to witness a pretty spectacular disaster that shows you exactly how dangerous waves can be when we don't understand them. It all starts with a pretty simple question. I mean, we all know that a strong wind can push things over, that's obvious. But what if it doesn't just push? What if it sings a structure to death? Well, this is exactly what happened to the Tacoma Narrows Bridge. The wild part is, it wasn't the raw power of the wind that brought it down, it was its rhythm. The steady gusts created these tiny vibrations, a wave, that just so happened to perfectly match the bridge's own natural frequency. The rate at which it just naturally liked to sway. And that brings us to the core concept here, resonance. The best way to think about it is like pushing someone on a swing, right? If you push it just the right moment, matching its natural rhythm, it goes higher and higher with almost no effort. Well, for the bridge, the wind's pushes were perfectly timed and those little vibrations just grew and grew and grew until the whole thing was catastrophic. So to really get a grip on this, we need to break down what a wave actually is.
So let's get back to basics. What's the fundamental blueprint of a wave? What are we really talking about here?
Okay, so waves basically come in two main flavors. First, you've got a transverse wave. This is your classic stadium wave, right? The people are moving up and down, but the wave itself is traveling sideways all the way around the stadium. But then you have a longitudinal wave. This is more like pushing a slinky. The compression actually travels forward in the exact same direction as the push. Sound, by the way, is a perfect example of this. It's just compressing air as it moves towards you.
All right, so every single wave has what's called a wavelength. The easiest way to think about it is as the wave's size. It's just the physical distance from the very top of one crest to the top of the very next one.
And then there's frequency. So if wavelength is the wave's size, you can think of frequency as its pace. Imagine you're just standing in the ocean. The number of wave crests that roll past you every single second, that's the frequency. And we measure this in something called hertz.
Now here's the cool part, where it all connects. The wave's overall speed, its velocity, is simply its frequency multiplied by its wavelength. And in any given medium, whether it's air or water, that speed is constant. This means wavelength and frequency have this inverse relationship. The longer the wavelength, the lower the frequency, and the other way around. They're always in balance.
And you've totally experienced this yourself. An echo, like when you shout into a giant canyon, that's a single, clean reflection of a sound wave bouncing back at you. But reverberation, what you hear in a big empty church or a gymnasium, that's thousands of those reflections bouncing off every single surface, all jumbling together into that lingering, continuous sound.
Okay, so that's the theory. But how in the world do scientists actually measure these invisible forces? I mean, how do you clock the frequency of a vibrating steel beam? Well, for that, we have to go to the lab. See, to figure out what happened to that bridge, you don't need to build another bridge. You just need a diving board. Or, the more technical term is a cantilever, which is just a beam that's fixed at one end. It's the perfect, simple model for studying how really complex structures vibrate.
And the experiment itself is, well, it's beautifully simple. You just clamp one end down, you add a known weight to the other, you give it a little push, and you time how fast it wobbles back and forth. This simple measurement lets you calculate its natural frequency, the exact same property that turned out to be so destructive for the Tacoma Narrows Bridge. Okay, so that's how you measure vibrations in a solid. But what about waves in a liquid, like sound traveling through water? Well, for that, scientists use a really clever trick that involves something called a standing wave. They use this device. It's called an ultrasonic interferometer. Big name, but what it does is pretty simple. It sends a sound wave up through a liquid. That wave hits a reflector at the top and bounces right back down. Now, if you tune it just right, the outgoing wave and the returning wave interfere with each other perfectly, and they create what's called a standing wave. It actually looks like it's not moving at all. And by simply measuring the distance between the peaks of this stationary pattern, you can figure out the original wavelength, and from there, the exact speed of sound in that liquid. Pretty neat, right?
So we've gone from a falling bridge all the way to the lab. Now let's see where this knowledge really takes us in the real world. This is where the physics gets incredibly powerful.
I want you to imagine you're in a submarine, deep, deep underwater. It is pitch black. How do you find your way around? How do you detect anything else that might be out there with you? Well, you use sound.
This is sonar, and it's a direct application of what we just talked about. The sub sends out a ping, and then it listens for the echo. And because we know the precise speed of sound in water, something we just figured out how to measure in the lab, we can time how long it takes that echo to come back and calculate the exact distance to any object out there.
Okay, now let's take that exact same principle, sending out a wave and listening for the echo, and apply it to maybe the most delicate environment of all, the human body. How can this same physics give us a window inside ourselves without a single cut?
The answer is ultrasound, and the key is right there in the name, ultra. We use sound waves with an incredibly high frequency. So why does that matter? Well, remember that inverse relationship we talked about? A higher frequency automatically means a shorter wavelength. And a shorter wavelength is like using a much finer tipped pen. It lets us create a way more detailed, high-resolution picture of what's going on inside.
Wow. So we have gone on quite a journey here, from a collapsing bridge all the way to a non-invasive view of a beating heart. So what's the thread? What connects all of this? The key takeaway here is this. Understanding the basic physics of wavelength, of frequency, and especially of resonance, it's not just some academic exercise, it's what keeps our bridges standing, it's what lets us navigate the oceans, and it gives us the power to heal. It really is the invisible architecture of our modern world. So I'll leave you with one final question that brings it all back home. We saw how the steady rhythm of the wind brought down a bridge. With that in mind, why is it a centuries-old military rule that soldiers must break step and stop marching in perfect unison when they cross a bridge? The answer is pure physics. Thanks for joining me.